to continue the progress of signal propagation, at another time delay that t equals to 2 times of L over Vp, that is, signal is going to the right-hand side and reflected to the left-hand side. Then with this time delay at z equal to 0, that is the very left-hand side of the transmission line system, you will find 2 signals, V plus and V minus plus, okay? The first V plus signal is generated by the battery, by the generator. The second signal is the reflected signal of the reflection at the right hand. So it is referred as V minus plus. That's the secondary reflection signal, which is due to the mismatch on the left-hand side. So if Rg equal to Z sub 0, there will be no mismatch. The V minus plus signal will goes to 0. On the other hand, if Rg is not the same as V sub 0, then due to the mismatch, you will have a non-zero V minus plus signal, okay? Now, then if you have mismatch on the left-hand side and the right-hand side, then you will have an infinite series of reflection. Does that mean we need to continue to calculate that forever? No. Why? Because eventually the reflections will go to 0, because reflection coefficient for passive components. 什么叫 passive components？ 不插电的元件都叫 passive components。For passive components or passive transmission line, for passive component, the reflection coefficient is smaller than 1. Is smaller than 1. So eventually, the magnitude of the reflection signal will approaches to 0. Okay, now then you will have a converged solution. Okay, but anyway, at t greater than 2 times L over Vp, there will be 3 signals on the line: V plus, V minus, and V minus plus. That's the total voltage on the left-hand side on Z equal to 0. The total current will be I plus, I minus, and I minus plus. The current and the voltage will satisfy the boundary condition at the Z equal to 0. That is, V0 minus Rg times total current should be the total voltage. Then what can we do? We can substitute I plus I minus plus with this relationship and try to solve this problem. So you are recommended to do this yourself to see that the V minus plus can be represented with this equation and this equation. Okay? Oh, we already showed this equation because of this is the very first voltage signal due to this relationship. And the things in the red dash box is the reflection coefficient on the left-hand side near the generator. So again, the reflection coefficient is the impedance that you are looking to minus the impedance of where you are, Z sub 0, divided by Rg plus Z sub 0. Okay? Then let's take a look about some extreme cases. If the load resistance is 0, which means the transmission lines is connected to a short. What is the short impedance? 0. Okay? Then the reflection coefficient will be 0 minus z sub 0 divided by z plus z sub 0 equals to -1. So the reflection coefficient for short circuit is -1. And RL equals to infinity. That's open circuit. Okay, for open circuit, the impedance, the resistance approaches to infinity. So the reflection coefficient becomes infinity minus z sub 0 divided by infinity plus z sub 0 equals to 1. Okay? So as you can see, the reflection coefficient for short circuit line and open circuit line are quite the same. You see, are they the same? One is 1, the other is -1. They are not the same. Well, they have the same magnitude. And it means all the incident power are reflected. All the incident signal are reflected. The reflected signal magnitude is the same as the incident signal magnitude for both short circuit line and open circuit line. The only difference is there is a 180-degree phase difference for the short circuit line. For the open circuit line, the reflex signal has the same magnitude and the same phase as the incident signal. 对于开路来讲，打进去反弹的讯号跟打进去的讯号一样大，而且还同相位。但短路的线的讯号反弹的讯号跟打进去的讯号一样大，但是差180度。那反弹的讯号跟打进去的讯号一样大是什么意义 ？What is the physical implication for reflection coefficient magnitude equals to 1? If the reflection coefficient magnitude equals to 1, then it suggests there is no loss on the load. The load didn't dissipate any power. All the energy are reflected if your reflection coefficient magnitude equals to 1. Okay? Because short circuit and both short circuit and open circuit do not absorb energy. 短路跟开路都不吃能量，所以假如你的传输线的终端是接到短路或者是开路的话，所有能量都会反弹。来补充说明不只是短路跟开路不吃能量，只要你的终端负载是电感或者是电容的时候，它的反射系数会是多少？它的反射系数是 J 跟负 J。magnitude 一样等于1。因为电感跟电容也不吃能量，它会储存一些能量没有错，但是它本身不消耗能量。当然说你说真实的电感不吃能量吗？会啦，真实电感会吃一点。真实电容不吃能量吗？不太吃啦。只要你是纯电感、纯电容的话，那其实并没有能量的损耗。纯电感跟纯电容只是能量的储存，它没有损耗，所以它的反射系数的大小都是1，但相位有所不同。那至于short circuit跟open circuit 的话，它的相位要么0度，要么180度。OK， 所以反射系数这个东西，我们刚才也提过了对于被动元件来讲，反射系数小于等于1。等于1的话，表示所有的能量都反弹；小于1的话，表示什么？有些能量反弹，有些能量没有反弹。那没有反弹的能量，要么被你的负载吃掉。我们这边看到的是你有接一个真实的负载，但是未来我们会看到，它也可能不是负载，而是另外一段传输线。所以假如你的反射系数小于1的话，表示你的能量被后面的传输线给吃掉，继续往下去传下去这样子。所以从反射系为什么要各位把反射系数的定义背好？ 因为从反射系数你可以知道前面这一段跟后面那一个负载，或者是后面那一段传输线之间的关系。Okay? Now, the third extreme case that we will look into is the RL, the load resistance equal to Z sub 0, equals to the characteristic impedance of the transmission line. This is a special case of a match load, 匹配负载. This is a special case of matching load. Matching load. Then, according to the reflection coefficient definition or equation, the reflection coefficient equals to what? Equals to 0, which means all the incident power, all the incident energy are absorbed by the matching load. Are absorbed by the matching load. There's no reflection. So if you are connecting the transmission line to a matching load, then you will only have V plus, I plus signal going from left to right. Then you have no V minus, I minus signal, because you have a matching load. So all the signal will go from left to right, goes on one direction. Okay. So let's look at the example 6.1, which will teach you how to utilize the so-called bouncing diagram technique for time domain analysis of a transmission line. This example worth 30 points in your second midterm. Every year you will have a question, a problem like this. So be sure to check out the sample question. You will see something similar to example 6.1. So of course, you need to work on example 6.1. You need to work on homework similar to, that is related to the bouncing diagram, and you need to work on sample problems. Then you will have a great chance to get this 30 points in your midterm number 2. Okay? 好了，我拢讲到这明啊，对不？所以这一点也扣了啦。然后我们大概那个题型大概就是那个样子了，但是数字不会一样啊。对不对？我要数字还出一样的，那就太不尊重各位台科大的同学了，对不对？好。So let's look at the transmission line system we have here. It's still a DC source. So you have a 100-volt battery. The internal resistance of the battery is 40 ohm. The characteristic impedance of the transmission line is 60 ohm. And instead of writing the length of the transmission line, the length of the transmission line is described in terms of propagation delay. That is 1 microsecond. What is the 1 micro? What electromagnetic? How far can electromagnetic wave propagate in 1 microsecond? 一个 microsecond 电磁波可以跑多远？一个 nanosecond 可以跑多远？能有30公分。OK， 大家已经开始培养出电磁学的直觉了OK， 往下看就会看到30公分OK， 我说你的脚丫大小了OK， 好。然后嘞，然后一个 microsecond 呢，也就是30公分的1000倍啊，300公尺。所以一个 microsecond 电磁波可以跑300公尺。然后一个 millisecond 电磁波可以跑300公里。所以一个 second 就是30万公里。大概这样。所以假如他写1 microsecond， 当然啦，空气的传输线才是300空气传输线才是300公尺啦。只要你是那个 coaxial cable 啊，或者是 microstrip line， 那个距离就会比较短，因为跑得比较慢。All right, so in this problem, we describe the transmission line length in terms of propagation delay, which means that the signal goes from left to right will take 1 microsecond. And the load impedance is 120 ohm. 120 ohm. So the first thing you can do is what? Let me check. Is write up the some basic information about the transmission line system. For example, you should write up the reflection coefficient at the load. What is that? 120 minus 60 divided by 120 plus 60, that will be 60 over 180. That would be 1/3. Okay? So you need to calculate the reflection coefficient to the right. Reflection coefficient to the left, that would be what? 40 minus 60 divided by 40 plus 60, that will be minus 20 over 100. So that will be minus 1/5. So you first thing is to find out the voltage reflection coefficient on the right and the voltage reflection coefficient on the left. And it also shows you the V plus signal. So at the time equal to 0, when the switch is closed on, the V plus positive going signal will be what? That will be 100 ohm divided by 40 plus 60 over 40 plus 60, so that will be 60 volts. 用分压公式 So the V plus signal will be 60 volts, and reflection coefficient on the right and left hand side are minus 1/5 and 1/3. So here we try to prepare the bouncing diagram. So we draw this plot, and I will show you this. Okay, so the bouncing diagram begins by drawing a horizontal line indicating the location on the transmission line. So the left hand side is Z equal to 0, and the right hand side is Z equal to L. We also draw two vertical lines on the two ends of a horizontal line. They are the time axis. So t equal to 0 on the very top, and t becomes larger and larger as you go down to the plot. Then you should draw the reflection coefficient looking to the source, and the reflection coefficient looking to the load. So which are minus 1/5 and 1/3 respectively. Okay, then we add up the V plus signal. So the V plus signal, that's the initial signal, initial positive going signal, which is 60 volts in this case. It will goes from left to right, and it takes how long? It takes 1 microsecond to reach the right end. So here we mark the time axis as 1 on the right hand side. And what is the reflex signal V minus? V minus will be V plus times the reflection coefficient at the right hand side, which is 1/3, so that will equals to 20 volts. So the V minus signal going from left to right is 20 volts. Not because the source is a battery, so it's a constant DC source. The V plus signal, the V minus signal will stay on the transmission line all the time. Now, after t equals to 0. If the source is not a DC one, say a pulse signal, then the V plus and V minus signal may not appear on the line all the time. We will have kind of this problem in the homeworks or follow-up problems 所以小心啦，这边这个 case 是相对容易分析的，因为它用的是一个 DC 电源，但它也可以是脉冲或者是方波的讯号源。只要是方波或脉冲讯号源的话，那你就要小心了，它的出来的讯号所出现的时间就不会一直在上面，而是出现一小段时间。那个类题会在课本的后面的这一章后面的习题里头会有类似的题目。All right, and here we marked here as 80 volt. Why? Because after the time equal to 1 microsecond, on the right hand side you will observe V plus signal and V minus signal at the same time. Now, for t greater than 1 microsecond, on the right hand side you will observe V plus signal and the V minus signals, which is 60 plus 20. So we mark 80 here. That is the total voltage you observe at Z equal to L. Now, so if t is smaller than 1 microsecond, the total voltage observed here is 0. And between 1 and 3 microseconds, the total voltage here is 80 volts. Okay? On the other hand, between 0 and 2 microseconds, the total voltage observed here is 60 volts. What is the total voltage observed here at t greater than 2 microseconds? How many terms will you see here? You will see V plus, V minus, and V minus plus. You will have 3 voltages. What is V minus plus? That would be 20 times 1 minus 1/5. So that would be minus 4. Now, what is total voltage here? Between 2 to 4 microseconds. That would be 60 plus 20 minus 4. 76. 76 volt on the left hand side. Okay, so you have 76 volt on the left hand side, and the V minus plus signal is minus 4 here, going from left to right. Then at 3 microseconds, it will observe V plus, V minus plus, and V minus plus minus, which is minus 4 times 1/3. That would be minus 4 over 3. So the total voltage between 3 to 5 microseconds at the right hand side is 224 over 3. Okay. 70几啦，70几啦，OK。80减4再加这个东西会再少一点嘛，70几吧，那当然你可以继续下去嘛，So the process can be continued to find out following V minus plus minus plus signal and V minus plus minus plus minus signal like this, and you can add up to find the total signal. Okay? So you can continue this on and on and on. And we are interested to find out if you draw a line parallel to the time axis, you can find out the time signal variation on the time domain for a specific location. For example, if you draw the voltage variation along the red line here, you are looking at Z equal to 0 location, position of Z equal to 0, and see what the voltage changes as the time as the time increases. So between 0 and 6, you observe 60 volts. Between 2 and 4 microseconds, you observe 76. And between 4 to 6, you observe this number, okay? Can you tell me what is the eventual number of this thing? 75. Why? Yeah, because eventually this is a simple DC circuit. And one important thing is the transmission line effect only appear during the transient analysis, during the transient period, okay? So the variation in terms of voltage and currents only present for a very short time. So as the time, as we observe the circuits longer and longer, the transmission line effect shall disappear. You will only see the basic elements of the circuit. So for this circuit, on the left-hand side, you have 100 volt and 40 ohm resistance, and on the right-hand side, you have 120 ohm load resistance. So if you ignore the transmission lines, that will be 100 volts of battery connected to 160 ohm resistance. So the total current will be 0.625 amp. And the total voltage across the load, or at this point, will be 75 volts, right? So that is the so-called saturation. 等一下，当你观察的时间够长的时候 ，transient behavior 就会消失，然后你观察的就是 saturation 的那个现象。那个现象其实就是把 transmission line 直接拿掉，就可以得到。所以 eventually 整条传输线上面的总电压都会是75欧姆，整条传输线上面的电流都会是 0.625 安培，可以吗？所以这一种 transient 这个其实是一个 DC circuit 啦，所以当你观测的时间够长，它最终还是会变成 DC circuit 的形态。但是你会发现在最初的几根 microsecond 里头，它并不是 DC circuit 并不是 DC circuit， 并不是 saturation 状态底下的那些电压电流值而是会有一些有趣的 transient behavior。Alright, so if you write the voltage variation on the left-hand side, that would be this, and you see it will eventually approaches to 75 volts. In the middle, you see the voltage shows up at t equal to 0.5 because it takes half microsecond for the V plus signal to get to the middle of the transmission line. And it will observe follow-up voltage signal. V plus equals to 60, V minus equal to 20, V minus plus equal to minus 4, and so on and so forth. And you can observe that this thing will eventually saturate at 75 volts as well. And if you draw a horizontal line like this, then you will see the voltage distribution across the transmission line at a certain time instant. For this case, if you draw the red line which corresponding to 2.5 microsecond, then you will observe on the left-hand side, the total voltage is 76 because you see V plus, V minus, and V minus plus. On the right-hand side, you observe 80 volts because you see only V plus and V minus, not the V minus plus part. So if you draw a horizontal line, you can check up the spatial variation of the voltage on the line at a specific time instant. And if you carry on the voltage bouncing diagram and the current bouncing diagram, you see the overall system will saturate to a specific voltage, that is 75 volts and 0.625 amp on the whole transmission line. Okay. And yeah, so with enough observation time, all the voltage and all the current value will approach to the same one on the transmission line, because with several bounces, the signal that goes back and forth in the transmission line knows that, oh, on the left hand side is on the right hand side is a 120 ohm load, on the left hand side is a 40 ohm load. Then our overall behavior, our total voltage and total current during the saturation phase will be determined by the resistance or the impedance on the right hand and left hand side, not determined by the transmission line's characteristic impedance. Okay? Because eventually this is still a DC circuit. Okay? All right. Then, so here's one. Okay. So 我一直讲错哦，它不是 saturation， 这个叫做 steady state。OK 就是趋于稳定状态，稳定状态叫 steady state。OK 记下来SS steady state。So at a steady state, the V plus signal. So here's one interesting thing. So if you add up only the V plus signal, that is 60 for V plus, -4 for V minus plus, and 4/15 for minus plus minus plus. Okay? So you add up then, which is an infinite series, it will approaches to 56.25 volts. And the saturation state of I plus current at the saturation state will be 0.9375 amp. They still abide the 60 ohm characteristic impedance rule for the positive going signal. For the negative going signal, the total voltage at the saturation steady state will be 18.75. The total current of I minus components at the steady state is -0.3125. And you see they still maintain a 60 times ratio, a ratio of 60. So the positive going part and the negative going part are all consistent with the characteristic impedance of the transmission line. However, if you add up the total V plus steady state signal and the V minus steady state signal, that will be 75 volts, and the ISS is 0.625, which is not consistent with the 60 ohm ratio of the transmission line. So at the steady state, the total current, the total signal, which combines the positive and negative going part, is irrelevant to the characteristic impedance. Nevertheless, if you just look into the total V plus signal and the total V minus signal, they still abide the characteristic impedance relationship of the transmission line. Okay, so that's an interesting fact. So at the steady state, the total voltage and the total current on the line is the same as lump circuit analysis. During the steady state, the transmission line effect will have, the transmission line will have no effect on the steady state voltage and current of this DC circuit. Why? Why? 这下面这句话蛮有趣的哦。The series transmission line 是什么？还记得我们这2天在讲 transmission line， 它的 what is the distributed circuit model of the transmission line? Series inductor, shunt capacitor, series inductor, shunt capacitor, series inductor, shunt capacitor. So during the transient state, that is, the switch is closed, the voltage starts to charge up the circuit. The inductor is charged up, the capacitor is charged up. So what happens when the inductor is charged? It becomes a short circuit. What happens when the capacitor is charged up? It becomes an open circuit. So for this distributed circuit model, if both the capacitor and the inductor are charged, it will become short circuit, open circuit, short circuit, open circuit, short circuit, open circuit. Then once you reach the steady state, the transmission line is simply a short line connecting the left and right hand side of your circuit. So it plays no, you have no effect on the steady state voltage and current. Okay? So you should look into the descriptions in the textbook. All right, so that's the total voltage we observe at a certain point for. Yeah, I already looked into this. Okay, T equal to 2.5 microsecond, and T equal to 1 times 1 and 1/3 microsecond. That's the total current distribution on this specific time instant. And okay, the next thing is, in example 6.1, we're introducing the bouncing diagram for a constant voltage source. And of course, we don't necessarily need a constant voltage source. We can apply a voltage source such as a pulse signal or a step wave. Okay, so in this case, the source signal, the generator is replaced with an impulse function, which has a magnitude of z sub 0, but the signal only appears between 0 and t sub 0. So the signal only appears for a certain amount of time. So it only appears between t equal to 0 and t sub 0. This pulse function can be regarded as a subtraction or addition of two step functions. There will be this step function and this step function. So if you add it up, the two step function will end up with this pulse function. 你把2个 step function 叠加在一起，就形成这样子一个在0到 t0 之间，然后大小为 v0的这个讯号。所以 in example 6.2, you can redo the bouncing diagram. You can redo the bouncing diagram for the same circuit. However, the 100-volt signal only appears between t equal to 0 and t equal to 1 microsecond. So the bouncing diagram becomes a little bit interesting because at any instant, you only observe just two components of the V plus, V minus, V minus, plus, minus, plus, minus terms. You do not see all the terms, okay? So on the left-hand side, at between t equal to 0 and 1, you got 60 volts. Between 2 and 3 microseconds, you have V minus and V minus plus, so that would be 20 plus minus 4. So you have a total of 60 volts over here only. And here you will have 4 plus 4 over 15, minus 15 or something, okay? Did you observe something from this bouncing diagram? The signal is become smaller and smaller, will eventually goes to what? Goes to 0. Why? Because the source only provides signal for a finite amount of time, which means the energy provided by the source is finite. However, on the two sides of the circuit, on the two sides of the transmission line circuit, you have a resistor of 40 ohm, another resistor of 120 ohm. They will absorb the energy, absorb and dissipate the energy. Do transmission line dissipate energy? 中间那个传输线会不会损耗能量？不会哦，至少我们目前看到的不会哦。我们目前看到的都是理想传输线啊。虽然你说它是60欧姆，但它不是真的60欧姆。那个60欧姆是什么？电压跟电流的比值。那个60欧姆的理想传输线是不耗损能量的，所以能量被谁吃掉？左边的电阻跟右边的电阻。所以当它打到左边跟右边的时候，能量会有部分反弹，但大部分会被吃掉了。一大部分会被吃掉，所以左边吃掉一点，右边吃掉一点，左边吃掉一点，右边吃掉一点。Eventually， 你最后的那个传输线上的讯号会变多少？趋近于0嘛。你当然可以倔强的说 ，the signal will appear on the line forever。OK， 当然你可以说 forever， 但 well。From the perspective of engineering, then it will goes away in a few bounces. All right? So it will approach 0 anyway. So in the steady state, which means after a few microseconds, there will be no signal on this resistively loaded transmission line. Okay? So, yeah. So this using the bouncing diagram, you can draw the time variation of the voltage signal on the left-hand side, and here's the time variation of the voltage signal on the. This is the left-hand side. This is the right-hand side. This is in the middle. Okay. And you see they all approaches to 0 as we goes from transient to steady state. If you draw a horizontal line on the bouncing diagram, then you can observe the signal distribution, the voltage distribution across the transmission line at a certain time instant. So, for example, at t equal to 2.25 microsecond, you have the V minus plus signal just appear, while the V minus signal have 75% remain on the line. So if you add up the V minus signal and the V minus plus signal, you end up with this result. Okay? So that will be the total voltage on the line at t equals to 2.25 microsecond. Okay, that shall conclude our lecture for section 6.2.